All right, one more day of review, you guys. We're going to review Module 3. We won't bother reviewing Module 4 tomorrow because we just did it. We'll actually move on to Module 5 tomorrow. So Module 3, in my opinion, the most important of the modules that we do in 7th grade. You learn the most important skill that you learn in 7th grade, math, I should say. I don't want to say it's more important than other subjects you learn, which is solving like single variable, two-step equations using the properties of equality. And so, well, how did we get there? Well, the first thing we did is we started looking at just algebraic expressions, or expressions that contain variables. So let me just come up with like a generic expression here, maybe like 5a minus, I don't know, how about 4b plus 12? And then oops, sorry, I'm off the screen. And we talked about like the pieces of these things. So each one of these things is called a term, right? Each thing that is separated, or I should say, each addend in the expression. So each thing that's being added is a term, and so each one of these things is separated by an addition sign. Oh, Mr. Thomas, this one's separated by a subtraction sign. Yeah, but subtraction is just addition. So if I say an addition sign and you see a subtraction sign, same thing. Okay, and then within each term, there are pieces as well. So this number right here, the 5, and this number right here, the -4, right? Because I always think of, when I see minus 4b in my brain, I'm thinking of it as plus -4b. These are the coefficients of those variables, the numbers that are multiplying by the variable. And then obviously, like I just said, that these two here, the a and the b, they're called the variables. And then this over here, this last term, it's called the constant term. Because remember, in math, things that remain constant means they don't change. And this one, it doesn't have a variable in it, right? So it can't change value. It's just always going to be a 12. So we call it the constant term. All right, and then we wanted to be able to write equivalent expressions, right? How can we take expressions and change them into different forms, or how they look, while maintaining their value or their meaning? And so we learned about these different forms of expressions: standard form and factored form and expanded form. And we wanted to be able to go between these freely using a couple of skills. The first skill that we learned was combining like terms. Combining like terms. And the like here is short for alike, terms that are alike. And terms are alike if they have the same variable. And there's a little bit more to it than that you'll talk about in 8th and 9th grade for. But for our purposes right now, if they got the same variable, they're like terms. And so let's say you had this expression. How about 9x plus, I don't know, 4x minus 6y minus 12y plus 3. And we wanted to combine these like terms and write this expanded form expression. It's expanded because it has multiple like terms that could be combined, and write it in standard form, which means it's fully simplified. All its like terms are combined. It's written conventionally. So let's do 9x plus 4x. We just combine the coefficients, so that becomes 13x. And then this gets a little tricky here because we got these minus signs here. Remember, we make fewer mistakes if instead of thinking of subtraction, we think of each of these terms as adding the inverse. So I'm going to think of this as plus -6y and plus -12y. And so what I have here is -6y plus -12y. That's -18y. So I'll write it as plus -18y. And then the last thing here I have is the constant term, which is 3. And there's no terms that it can combine with. There's no other terms that don't have a variable, so it has no like terms to combine with, so I'm just going to write plus 3. And then we're sure to not combine the 13x and the -18y because they're not like terms. You can't combine x terms and y terms using addition or subtraction. You can multiply them. We're not doing that yet. Not really. So, all right, and then another way that we can move from one form of an expression to another is using the distributive property. That's when you have, a factored form expression, of an expression that's written as a product of two factors. So maybe you got 4 times the quantity of, 6x minus 2. Okay, so normally if we were working with PEMDAS and we had just all like known values, numbers instead of variables, we could just do the math inside the parentheses first, do 6 times whatever this number is, subtract 2, and then multiply by 4. But we can't do that when we don't know what x is. So if we had a larger expression or another equation that we were working with, this was inside, we'd want to break these values out of this parentheses so that we can do some other things with them. And we do that by distributing the 4. And we get 4 times 6x equals 24x. And 4 times negative 2 is negative 8, which I'll write as minus 8. And so these two expressions that I've written on the opposite sides of these equal signs are said to be equivalent expressions because they would give you the same value no matter what x is if you were to evaluate them. Remember, when you put a number in for the variable in an expression and then you figure out what it equals, you do all the math, that's called evaluating. All right, and then the last one that we learned a lot about was just the reverse of the distributive property, which we called factoring. And so that's if, like, let's say you had an expression that was written in standard or expanded form, and maybe it was something like, how about 9w plus 12g minus, how about 42? And I wrote that very specifically because I wanted each term in there to have a factor of 3 inside of it. And so since I know that there's a common factor of 3 between the 9, the 12, and the 42, I can factor out that 3, write it on the outside of this quantity I'm about to create, and then the terms inside this quantity in the parentheses is just going to be what's left when I divide each of these terms by 3. So 9w divided by 3 is 3w, 12g divided by 3 is 4g, and negative 42 divided by 3 is negative 14. And so these two expressions that I've written here are equivalent, just this one's in standard form and this one's in factored form. And this one can be useful for solving equations, especially later down the road when you get to more complicated stuff than what we're doing in 7th grade. All right, so once we were pretty good with our expression skills, we had to move on to equations because that's where expressions are used the most. That's what we really want to be able to do is solve equations. So we started with some really silly basic equations. We started talking about, well, does 3 equal 3? And you all went, yes, Mr. Thomas, you're super boring. And then I was like, okay, well, what about, does 4 equal 3? And you were all like, no, oh my God, I hate this class. Yeah, okay. Oh, I'm off the screen again. Well, the point of this was to talk about the fact that equations are just statements. They can be true, like this one over here, and they can be false, like this one over here. And what we care about most of the time is when are they true, and what numbers make them true, and what operations are we allowed to do to them that still make them true or keep them true. And that's where these things called the properties of equality came through, where I did this really boring thing where I was like, okay, so if you start with a true equation, you can add the same numbers to both sides and you get 5 equals 5, and that's still a true equation. And I did that with addition and subtraction and multiplication and division, and that gave us the properties of equality, which is essentially the rule or the idea that you can add, subtract, multiply, and divide both sides of an EQ, both sides of an EQ, short for equation, by the same number, and it stays true. Assuming it was true to begin with. It was a true equation to begin with, it will remain true. And the EQ remains true. You never really use 0 to multiply or divide though, or really to add or subtract, because if you add or subtract 0, it doesn't really do anything, and if you try to multiply or divide by 0, you're just going to wind up with some weird stuff. So maybe I should say non-zero number, but whatever, we'll let it slide. All right, and so that's our basis for solving equations. We use the properties of equality. We add and subtract and multiply and divide to both sides in order to isolate the variable. That's this big idea. Isolate, remember, means to get it by itself. We want that variable by itself. And so that's our goal. Isolate the variable. And so if you get an equation that says x equals 4, well, there's nothing to do there, right? Because the variable is isolated. It's by itself. X equals 4. Done. But what if you get one that says, I don't know, 3x equals, how about 30? Let's make it easy on ourselves. All right, well, the variable is not isolated this time. It's got this 3 with it. So what we do is we think about, well, what operation is the 3 doing to the variable? It's multiplying. Okay, so in order to isolate the variable, to get it by itself, we want this 3 really to be a 1. So it says 1x equals something, right? Because 1s we don't even write. They're just like not even there. Okay, well, we want to turn a 3 into a 1. Let's just do the opposite operation of what we see. We see 3 times x. Let's divide by 3. So now we have 1x like we wanted. But the properties of equality say we have to do it to both sides of the equation to maintain that balance. And so we get x equals 10. All right, and so that's what we call a one-step equation because it only took me one property of equality step right here, this one step, to solve. So let's do a two-step. What if we had negative 4x minus 12 equals, how about 48? Is that going to work out for me? I want a whole number answer. I don't feel like going to fractions right now. Yeah, that'll work out. Okay, so I look at what's happening to the variable here. I see that it's being multiplied by negative 4 and 12 is being subtracted, or negative 12 is being added, however you like to think of it. And if I knew what x was, I would multiply by the negative 4 first, then subtract the 12. Well, in order to solve, in order to isolate, we always work backwards. We work in the reverse order of PEMDAS, or the reverse order we would if we were evaluating, and we do opposite operations. So there's two things we got to remember: reverse order, or reverse PEMDAS, and opposite operations. All right, so since I would subtract the 12 last if I was working in PEMDAS, let me get rid of it first by adding positive 12 to both sides. And so negative 12 and positive 12, they make 0. They cancel each other out, as mathematicians love to say. And so what is left is negative 4x equals 60. And then now I need to divide both sides of this by the number I see multiplying by the variable, or the coefficient in this case. And so I want to divide both sides not by 4, but by negative 4. If I divide by 4, I'm left with a negative x, which isn't necessarily a bad thing, but just leaves you an extra step. So on this side, I'm left with x, because negative 4 divided by negative 4 is 1. So really we have a 1x here. We just don't normally write it. And then 60 divided by negative 4, well, 60 divided by 4 is 15. But I know that a positive divided by a negative makes a negative, so I got negative 15. So that's our solution to that one. And so this was the bulk of what we needed to do, but it wasn't the big challenge. Once we were really good at our expressions, and we got this algorithm of solving equations through isolating the variable using the properties of equality down, we got to the real work of Module 3, which was applying those skills to solve these pretty challenging word problems. And there's one in particular that every year always is like the kind of the monster one, and it's this one about Julia and Keller and Israel, the firefighter, volunteer, fundraiser, collector people. And I'm going to redo this question here for you so that you can kind of remind yourself of how we have to define a variable when we read the information, and then we have to determine which value we know the least about and kind of make that our variable, and then write the other unknown quantities in the question in terms of that variable, meaning using the same variable. Then we have to create our own equation that represents the situation. Then we have to solve it, and then make a conclusion based on what we saw when we solved. So this was the big work of Module 3. Let's do it. It says, Julia, Keller, and Israel are volunteer firefighters. On Saturday, the volunteer fire department held its annual coin drop fundraiser at a streetlight. The most pointless sentence in all of these books. I hate this sentence so much. Don't bother telling me that. Just give me the information I need. Okay, so after 1 hour, Keller had collected $42.50 more than Julia. Okay, so I know a little bit about Keller. Keller's green. $42.50 more than Julia. All right, and then Israel had collected $15 less than Keller. So Israel's information will be in purple, and I know a little bit about Israel. And then it says the 3 firefighters collected $125.95 in total. How much did each person collect? And then it says find the solution using tape diagram, but we're not doing that. We're working on our algebra skills. All right, well, they told me a little bit about how much Keller made. They told me a little bit about how much Israel made. They did not give me any specific direct information about how much Julia made. So let's make Julia, the money that she made, our variable, because it's the thing we know the least about. So J, the variable J will stand for money collected by Julia. We always define our variable right off the bat. All right, and so now let's write expressions for how much money Keller made and how much money Israel made using J, and then we can use those pieces to build the equation we need. So it says Keller collected $42.50 more than Julia. So if J is how much Julia made, then if we just add $42.50 to that, that will be how much money Keller made. And I'll write that as Keller dollars. Okay, and then for Israel, she collected $15 less than Keller. So I got to be careful here. I'm gonna use the Keller expression that says how much Keller made, and then I'm gonna subtract 15 from that, because that's what it says, right? Israel collected $15 less than Keller. So I took Keller's expression and subtracted 15 from it, and I'll just write Israel dollars next to that. All right, and now it says the total they collected is $125.95. So if I add these three expressions for how much Julia made, how much Keller made, how much Israel made, and set them equal to $125.95, I've got the equation I need. I'm going to try to write this relatively small and efficiently up here. So I got J for Julia plus J plus 42.50 for Keller plus J plus 42.50 minus 15 for Israel, right? So I had to have all three pieces, so I wound up with 3 J's in my equation here. And that's all supposed to equal 125. Oops, I don't know what, ignore that dot. That dot should not be there. 125.95. All right, and now I'm going to solve this moving downward right here in this space, and I'm going to try to make sure to keep my equal signs in line, right? Because that helps us keep everything neater and make fewer mistakes. So I start by combining my like terms. I got 1, 2, 3 J terms. And so I'm not going to write 3J way over here because that's going to make my whole thing kind of wonky. I'm going to estimate that I probably want it right about here to leave myself enough room for a number here, because I got to add my constant terms now. 42.50 plus 42.50, that's 85, right? Yeah, that's 85. And then I subtract the 15 and I get 70. So what I got here is 3J plus 70 equals, the equal sign's right in line, 125.95. Now I just need to solve using my properties of equality. I'm going to subtract 70 from both sides. I get 3J equals, I believe this is $55.95 over here. And then I'm going to divide both sides by 3 to get rid of that 3 that's multiplying by the J. And I get J equals, I want to say this is 1890 something. I don't know. Let's let the machine do the work here. What do we got? 55.95 divided by 3 equals $18.65. So Julia made $18.65. So this video is getting close to 20 minutes, so I'm going to go ahead and cut it off here. But you know how to finish it from here. If you wanted to figure out how much Julia made or Keller made, you would just take this number and add 42.50. And if you wanted to figure out how much Israel made, you would take the money you just figured out for Keller and subtract 15. All right, so I'm going to ask you to practice this a little bit today, and then we'll move on to Module 5 tomorrow.